So a couple quick reminders. Want to make sure that you have access to all of the resources that we use. So that includes Piazza. That's where all of these lecture recordings, lecture notes are going to be posted, as well as PDF versions of the homeworks and additional resources. Gradescope is where you're going to do all of the actual submission of assignments. That includes the written homeworks. It also has some quizzes, just kind of quick checks to make sure you understand the topic we're talking about. WebEx is where I post kind of quick notes about things that are happening. And then MATLAB Grader is where you have some of the problems which go into Gradescope. After you complete them on MATLAB Grader, you take screenshots showing that you completed them, upload those to Gradescope. So looks like a lot of you have enrolled in that. For those that I noticed this morning hadn't yet, I selected to resend the notification email. So it should be an email from MathWorks, might say MATLAB, probably says MathWorks, that is inviting you to the course. So you want to use the link that's in that email to add yourself to it. So if you don't see it, double check your spam folder. Sometimes, the filters do some weird things with some of the emails. So take a check there. If you still don't see it, let me know and I'll try and resend the message to you. One key note I want to make sure of, notes from previous TAs. So for Gradescope, you'll notice that for some problems, it allows you to upload a file. And so it will actually allow you to upload any kind of file, but please use PDF files, right? So these are going to be a lot easier for the TA to actually process. If you upload something like a text file or some weird extension, then the TAs have to download it, open it, figure out what's going on with it, and then go back to Gradescope. So if you can do a PDF version, that would be much appreciated. So then they can do all of the grading within Gradescope and they don't have to worry about that. And also, when you're doing a MATLAB Grader problem, make sure that you have the right format. So if you look at homework 0, it gives an example. So your screenshot should include the problem number, your name, and also all the check marks showing that you passed all of the tests associated with that problem. So you can see an example in that homework 0 of what that is going to look like for you. And so if you have it in that form, then you don't have to worry about losing points for those problems. All right, so those are my few logistical notes. If you haven't gotten the reference tables that you weren't here last time, I do have some copies with me, or you can stop by my office anytime next week and pick those up. So the idea is use them as you're working on the homeworks, get familiar with where the content is, what's actually on there. If you need to add little notes about things, you're welcome to do so. You're not allowed to put full problem solutions on those reference tables. All right, so going back to our material here. So there's a couple frequently used signals that we're going to be talking about a little bit here. All right, so last time we covered sinusoids and also exponential functions. We're going to see that those pop up a lot, especially once we get into our frequency domain evaluation. We're going to see exponentials quite a bit. But a couple other common ones is a constant signal. So hopefully pretty straightforward, just means that for all time, that our signal has the same value. And so if we were to sketch this signal, right, we just have a constant value for all time. And a related signal, which we're actually probably going to see even more than the constant, we're going to see it pops up in a lot of different ways, is the step signal. So because we come across this step signal so much, we're actually going to give it special letters that we're going to associate with that. We're going to call this a U for a unit step function. And it's defined to be 1 when the argument inside is greater than or equal to 0. And it's going to be 0 otherwise. And so if we were to sketch this signal, what it's going to look like, 0 for t less than 0. Then we jump up to 1 and stay 1 for the rest of time. And we can do like what we talked about last class. Is we can scale and add signals together. So say, for example, if I wanted to scale my step signal, then I can just multiply it by a scalar constant. And so all of the values that I have are going to get scaled by that same constant. And so what I get here is it's the same kind of shape, just we've scaled our magnitude. And I could take these signals, I could add them together. So I can see when t is less than 0, they're both 0. When t is greater than 0, we have 1 is 1, 1 is 2, we have 3 for t greater than equal to 0. All right, so it's a little bit easier when our change times match up between the two signals. We could have a case where, say, one changes at 1 instead of 0, in which case, when you add the signals, you're going to have more cases here that you need to account for. All right, so scaling and adding, those are the most basic things that you can do with signals. But there are a lot of other things that can happen to our signal that we want to be able to understand how they work. Right, so there are 3 main ones here that we're going to look at that all relate to the time axis of that signal. So what we can do is we can shift our signal in time. Right? So an example like this, we could say instead of this step change occurring at t equals 0, maybe we shift it to the right and we have a step change at some other time, or we could shift it to the left. We can also do a time flip or a time reversal. So essentially we take our signal and mirror it about that vertical axis. And we can also do time scaling. Right? So this one looks a little bit more interesting. And we'll see, say you have a signal like this. Right? So we could compress that signal in time. So we have the same kind of shape, but the time that it happens is much narrower. Or we could also have a case where we expand time and we have the same kind of shape, but you can see that the area that covers in time has increased. Okay, so we're going to look at each of these separately, and then we're going to see what happens when we do a combination of these changes in time. So first one is time shifting. So let's say that I have a time signal here, x of t. And let's say I'm shaped something like that. So let's say that I want to apply a time shift. So the way that we're going to capture that time shift, we're going to generate a new signal, y of t, which is related to x of t with some constant shift in time. And so this is one of those where it might seem a little counterintuitive at first when you're looking at it. Once you do a few examples, hopefully you can convince yourself of the fact that it seems a little counter, because we see this negative sign here. And it turns out that that negative sign, if say tau is a positive number, is going to result in a shift to the right, where instead of this step change here was at 0, now it's going to be at tau, where this was at t, it's going to be at t plus tau. So if we have it written like this, then if that tau is positive, we consider that to be a time delay or a shift to the right. And if that tau is negative, so you'd end up with a t plus some number, then we consider that to be a time advance, resulting in a shift to the left. Yeah, so definitely looks counterintuitive at first. So let's take a look at one of our examples here. So let's say that we had u of t minus 1. Right, so what we saw before is that u of t is 1 when t is greater than or equal to 0, and 0 otherwise. So if I was to make a plot of this, right, so our u of t looks like that. So one way that I can think about this is I'm going to temporarily rewrite this as a u of x, where I can use the same format that I had here. Okay. So now that we kind of got that t away from here, we can see this is the same thing. All we did was change the variable that we're using. Now I'm actually going to substitute in my t minus 1 for x. So we have 1 and 0. So instead of x, we have a t minus 1 greater than or equal to 0. But I need this to be strictly in terms of t. So inequality rules, I can add plus 1 to either side of the inequality. So this is equivalent to t greater than or equal to 1. So when I sketch my signal here, for 0 for t less than 1, 1 for t greater than 1. Right, so it does seem a little counterintuitive at first. We see this minus sign here, you might think that it's a shift to the left, but it turns out when you have a negative number here, it's actually going to be a shift to the right. Right? So definitely one of those, as you see it a few times, kind of do this sort of comparison, plug things in, convince yourself that is the case, that positive is a shift to the right, negative is a shift to the left. And a way that we can do a quick check of that, right? So we know, say, looking at y of 2, right? We substitute in t equals 2 into that y of t, u t minus 1, right? So that's our output signal. We substitute in. You see we have u of 1. We know u of 1 is 1. And you can check that for multiple points in your signal. Right, so for something like this, u of t, it wasn't as bad to do this substitution in here. For some, if you have a more complex signal, it might help to actually do substitutions and convince yourself that the output that you got actually corresponds to the relationship that you have described. And so what we'll say is that a lot of these signals that pop up, sometimes we'll actually use them as a way to rewrite more complex signals. And sometimes that can be useful for us when we're doing further analysis. So let's take, for example, if we had something like P of t, which is a combination of these two signals that we just drew here. So if I draw my u of t, like so, and if we draw our minus u of t minus 1, right? So we drew u of t minus 1. This minus sign out front is going to change the magnitude value. So 0 stays 0. Our 1 becomes a minus 1. And so when we add these two signals together, they're both 0 here. In this region, u of t is 1. Minus u of t minus 1 is 0. We're going to get a 1 in this region. And then in this region, we have 1 plus a minus 1, going to drop us down to a 0. So one of those where some people might be able to just look at it and be able to visualize in their head. Some, it might be a little bit more difficult to do that visualization. But I do also have graph paper and trace paper, so you'll see that that might be useful to you if you're someone who has a little bit more trouble visualizing, especially when we get into the more complex signal manipulation, that might be useful to you to be able to have that additional resource. So if at any point you feel like you need some of that, let me know and I have a little bit available. So now I have this idea where I have some signal here, which I wrote in terms of step signals, right? So instead of just writing it as, say, the bracket notation that we saw before, actually capturing it in terms of these other signals. I can do a similar kind of idea. Let's say I have a signal x of t. And let's say we're 0. We jump up to 1, down to minus 1, and back up to 0. And so what I could do is I could see if it's possible to write our x of t in terms of p of t. So part of this is relatively easy. If we look at our p of t here, right? So p of t is 1 between 0 and 1. And we can see that this part of x of t looks exactly like p of t. I say x of t has a p of t component here. And now this part, we notice it has the same width as p of t, right? The width there is 1, the width here is 1. In terms of the magnitude, well, what we've done is we've flipped the magnitude, right? So instead of it being 1, it's a minus 1. We have a minus p of t. But we also see that it's been shifted, right? So our original p of t went from 0 to 1. This one goes from 1 to 2, which means that we actually shifted it to the right by 1 unit. And a shift to the right means we're going to do a minus 1. And so that's one way that we could rewrite this signal. Or we can take it all the way back and say, can we take this signal x of t and write it in terms of the step signal? Well, I can actually use my relationship. So I have this in terms of p of t, and I have p of t already in terms of my step signals. So I can take my x of t here. I can substitute in directly for p of t from what I have. And now, what do I do for the time-shifted version? Right, so you kind of think of this like when you're evaluating a signal for different values, right? If you have, say, an x of t and you're looking for x of 2, then you substitute 2 in everywhere that you have t. We're going to use the same kind of idea here. I'm looking for p of t minus 1. So I'm going to go back to my original p of t, and everywhere that I see a t, I'm going to substitute in t minus 1. So here I had a u of t. I substitute in for t minus 1. I have a u of t minus 1. I substitute in t minus 1 for t, leave everything else in the argument. And so now I can simplify this a little bit. We only have one u of t. We have 2 of these u of t minus 1 terms, both with a negative. I have a negative 2 u t minus 1. We distribute our minus sign, we have plus u t, and I can combine those two arguments there. Right, so in this case, what we have is we have a step signal like so. Then we have minus 2 coming in here, so it's going to cancel out that 1, bring us that additional minus 1. And then this change occurs at t equals 2, which is going to bring us back up to 0. So good exercise to sketch those out. Convince yourself that this is the same as this, represents that. Right? So all the same signal, just slightly different ways of writing that same signal. And depending on what kind of analysis you're doing, right, it might be easier to have signals represented in certain ways. And this is exactly what we'll see just before the first exam when we talk about Fourier series. Another way that we can write periodic signals to make using them in the frequency domain easier. Right? So a little bit of kind of exposure of that idea. You can write one signal, represent it in multiple different ways. Doesn't change the signal, might make analysis a little bit easier. Right, so with this idea of time shift comes one key characteristic of signals. And this is one that hopefully you've heard before. So one that's tied directly to this time shift. So we can say that a signal, say x of t, is periodic if we have some number, capital T, greater than 0, such that x t minus t is equal to x of t for all t. All right, so one more reminder if you missed that last class, this notation means for all. So for any value of t that we plug in, looking at x of t versus this shifted x of t by this capital T, we should get the same values. So a good example of this would be something like sine. Right, so if you have a pure sine of t, then your capital T would be 2 pi. So if I shift to the left or the right by 2 pi or any increment of 2 pi, then my x of t minus capital T will exactly line up with x of t. And so since there's multiple capital T's that could do this, right? So in this example, it could be 2 pi, 4 pi, 6 pi, right? Any multiple of those. And what we do is we define our period to be the smallest of those capital T values to be our fundamental period. And then kind of a reminder, then our fundamental frequency is 1 over that minimum capital T that satisfies that. Yep. So if you shift, so this would be 2 pi, this is pi. All right, so let's say that we shifted this to the right by pi. All right, so then this part here is going to start at pi. Right, so you can see in that case, if you shift by pi, that it doesn't line up with the pink. But if I shift by 2 pi, right, so I take this, it's easier to look at this one, this is at minus 2 pi. Right, so if I take this point, shift it to the right by 2 pi, then this up is going to start at 0. Right, so you can see that the green in that case exactly lines up with the pink. Right, so it works for the 2 pi. Pi does not work because we can see that the values don't match for time. So even though, yes, these points do match, it has to be for every t. Right, so that is time shift. Right, so we can do time delays, time advances. The next one that we might be interested in, we hear it referred to as time reversal or doing a time flip. And so if we have, say, a signal x of t, let's say for 0, for t less than 0, we're going to go up to 1 at 2, kind of sort of triangle shape here. And now, if I want to do a time flip, then my resulting signal, let's call that signal y of t, is going to be equal to x of t. We're going to negate at t. Right? So what that means is, let's say I'm looking for what is y of 1. Well, y of 1 is going to be equal to x of minus 1. Right? And you can do that for each point in time. Or if you're good at visualizing, you can say, well, essentially what's happening here is I'm taking this signal and I'm flipping it about the y-axis. So now, where this change was going from 1 to 2, it's going to go from -1 to -2. And we have zeros everywhere. And this is another one, as you're learning how to do it, that using something like trace paper can be helpful, where you can actually draw out the signal, do the flip physically, and still be able to see what it looks like. And so it turns out that there's also some interesting characteristics of signals which are associated with this manipulation as well. So there's actually a couple characteristics here. Right, so they refer to how, when we do this time flip, the signal that we start with relates to our resulting signal. So the first case that we could have is when x of t is what we call an even signal. And this happens if, when you do the flip, it's exactly equal to that original signal. As an example of this, that's probably the most common one that we have encountered, is our cosine function. Right, so our cosine, note we have the symmetry, or at least we would if I could draw. And so if you take it and flip it about that vertical axis, then that x of minus t, cosine of minus t, is exactly lined up with cosine of t. So we consider this to be an even signal. So you can probably guess at what the counterpart is. Right, so if we call this signal even, all related on. And this is where, when we flip in time, it's actually the negative of that original signal. And so you can probably guess then, based on what we drew here, an example of that is sine of t. All right, so if I look at my original signal, sine of t, when I flip that signal in time, right, so I had lower here, this upper comes over here, so on and so forth. All right, so we can see that sine of minus t is exactly negative sine of t. So another way that we can look at it, if we take as another example, so let's say we have an x of t here. Which looks like this. So if I was to define this signal in bracket notation, my x of t is equal to 0 when t is less than minus 1, 1, or between minus 1 and 1, 0 when we're greater than 1. And so if I was to look at x of minus t, right, so what I do, everywhere that I see a t, I'm going to substitute in a minus t into this original form that I had. So my values here stay the same. They don't have a t dependence. But now this t becomes a minus t. Same thing happening here, like so. Right, and so maybe dusting off a little bit of inequality rules here. So I want this to be in terms of t, not in terms of negative t, so I can actually plot it out. So to get t isolated, that means I need to multiply both sides by that minus 1. But because we're multiplying by a negative, that's also going to change the direction of the inequality. So now this less than becomes a greater than, and my minus 1 becomes a positive 1. Same kind of idea here. So I'm multiplying through by the 1. So this becomes a 1. Less than becomes greater than. This becomes t. Less than becomes greater than, becomes a minus 1. And so if I compare what I have here, I have 0 for t greater than 1, same. We have 0 for t less than minus 1 is the same. 1 between minus 1 and 1 is the same. So it turns out x of t, x minus t are the same. And this is an even signal. Okay, so a way that we can evaluate that looking at bracket notation, or we might be able to visualize it actually looking here that we can do this split. So Similar kind of idea. Let's say we have an x of t which looks like this. Right, so doing the same thing I did up here, write this in bracket notation. So we have 0 when we're less than -1, t between -1 and 1, 0 greater than 1. Now in this case, if I do my substitution of minus t, so we have 0 for minus t, less than -1, which as we saw before, same kind of idea. We multiply through by that negative, get the equivalent inequality. Now notice that we have a value here, which actually does depend on t. So we need to do that minus t substitution here as well. So instead of that being t, becomes a minus t. It's going to be, for this case here, and then we have our last case. Right, so in this case, if I was to sketch out the signal, right, my x of minus t, we have 0, 0 here, and then in between -1 and 1, we're going to have negative t. So where we were at -1 for t, going to be a value of 1. At t is 1, and a value of -1. And we're going to have this kind of relationship here. And so what we can see in this case is that x of minus t is negative x of t. Is an example of an odd signal. And so what's kind of interesting is when you combine signals of certain types, that it gives you some intuition about what the output is going to look like. Right, so if, say, I have two signals, x and y, and my x is even and y is odd, if you multiply those two signals, your result is going to have odd symmetry. If they're both odd, then multiplying them is going to give an even symmetry. And if they're both even, then your result is going to stay even. And you can actually prove each of these by taking the definition that we saw previously. So let's take as one example, let's say we have a z of t is x of t times y of t. And x of t, y of t are both odd. Right, so I'm going to demonstrate this relationship here. Right, so for my x of t, y of t, I know that if those signals are odd, then x of t is the same as minus x of minus t. Likewise, y of t is the same as minus y of minus t. So now I have these two negative signs out front, going to cancel each other out. I'm left with x of minus t, y of minus t, which if I compare to what I have here, right, it looks the same, except I've replaced all the t's with minus t. So this exactly looks like z of t if I replace all the t's with a minus t. And since we have this relationship, we can conclude that z of t is an even signal. So give you a little bit of introduction when we're doing some of the proofs a little bit later, some of the ways that I tend to write things. So I tend to use this a lot just to mean like where we can conclude. So this implies that. So just kind of give you an introduction so when we get into doing those proofs kind of notation that I tend to favor when I'm writing these. Now, another interesting thing about this is if you do have a signal which is not even or odd, it turns out that you can actually rewrite it in terms of even and odd signals. Right? So you could have a signal which is not odd, nor is it even. But you can take any signal and rewrite it such that it is a sum of two signals, which are the odd and the even parts. So let's take as an example here, as I have my x of t, let's say looks like that. Right, so we can tell there's no even or odd symmetry, right? If we flip this about the vertical axis, right, it's not directly related to that original x of t. What we can do is we can define what we call the even of x of t, which we get by adding together x of t and x of minus t. Right, so if I do that, then what we're going to get is a signal like this, which we can see has that symmetry about the vertical axis. Okay, so we're taking from here right, so this is x of minus t, and adding that with our original x of t, having the magnitude. Similarly, we can look at the odd part of x of t. Right, so in this case, we're going to be looking at adding minus x of minus t. So we're going to get something like this. So we can see the odd symmetry kind of makes us think of sinusoid function. So we have this goes up, that goes down. So we flip it, it's the same shape, but negated in magnitude. And it turns out that x of t is equal to the even part plus the odd part, which we can see if we do a direct substitution. Right, so I substitute in for the even, 1/2 x of t plus 1/2 x of minus t. I substitute in my odd. You can see that the two negative t's here are going to cancel each other out. We're left with 1/2 plus 1/2 x of t gives us that x of t. So lots of different ways that we can manipulate our representations to make things potentially easier for us. So we'll see that when we're doing things like transforms, that kind of having this intuition that the single definition maybe is not the only way to represent this, that we can rewrite it in different ways, make the math a little bit easier for us, maybe in some points even be able to completely avoid redoing integrals that we really don't want to do. Right, so kind of motivation why we're talking about this sort of thing. All right, so next major thing that we might want to do with our signals is a time scaling. All right, so in this case, we take some scale factor. All right, we're going to say alpha is a positive number because we had that separate time reversal that we've already talked about. So in this case, right, this alpha is scaling the time axis. And this is another one of those that might seem a little counterintuitive at first, but it turns out that if that scale factor alpha is greater than 1, we say alpha is 2, 3, something like that, then what's going to happen is we're actually going to shrink the time axis. And if we're less than 1, we're going to be expanding that time axis. So, as that might seem counterintuitive at first, so let's take a look at an example here. Let's take x of t as 1 between 1 and 2. Right, so we can see here our non-zero width that we have is 1. Now let's say I take a case where my alpha is greater than 1. So let's say we have y of t is x of 2t. So it turns out what's going to happen is we're going to have the same kind of shape as what we had before. Except on the time axis, what we're essentially going to be doing is dividing by that scale factor. So where we had this at 1 is now going to be 1/2, where this was at 2, it's now going to be 1. And so we're actually going to get our non-zero region here as a width of 1/2. And so we've actually shrunk it in time. All right, so we can convince ourselves of that by taking a look at what's going on in the middle here. All right, so let's say y of 3/4. All right, let's smack dab in the middle of that. So y of 3/4 is equal to x of 2 times that 3/4 is equal to x of 3/2. I go back here. Right, that's my 3/2 value. And indeed, at 3/4, our y of t should be equal to 1. And we can use this same approach. Look at the case where that alpha is less than 1. So general shape is still the same. But now we're dividing our axis by 1/2, or in other words, multiplying it by 2. So this 1 is now happening at 2. 2 is now happening at 4. And that width that we see here is actually larger. We've actually expanded the time axis. So similar to the time shift, it's one of those that when you first see it, doesn't seem quite right. But once you do enough of them, do these substitutions to convince yourself, it turns out that larger than 1 alpha is going to compress the time axis. A smaller than 1 alpha is actually going to expand that time axis. So we've looked at each of these separately. So now the question is, what happens if I want to do a combination of these? All right, so maybe I want to scale, shift, and also flip with respect to the time axis. So let's take and see what happens if we do a shift, scale, then flip in time. Okay. So in the first output, I do my shift. So let's say this step is y of t. We take my original signal, x of t, we're shifting it by tau. And then I do a time scaling. Let's call this z of t. So I'm going to scale my y of t. Or if I relate it back to my original signal x, everywhere that I had a t, I'm now replacing with an alpha t. And then in the last step, I do a flip. So I'm taking my previous result, flipping it in time. Same as flipping that y. Flipping that t in x. Okay. So let's take a look at an example here. Okay, so let's say we have x of t is a triangle shape between -1 and 1. And let's say that I'm interested in knowing what is w of t, which is x minus 2t minus 1. Right, so if I follow this order here, the first thing I do is I'm going to shift. I can see that I have a -1 here. So we know that is going to be a delay or a right shift by 1. So my y of t same shape, but now I've shifted it to the right by 1. Next, I can do my scaling. So we have my scale factor. I'm going to ignore the minus sign because I'm going to deal with that separately as a flip. So we'll see a scale factor here of 2. So in scaling, we're going to shrink our time by a factor of 2. So this z of t intermediate step right, we're shrinking that in time. So 1 becomes 1/2, 2 becomes 1 because we're dividing by that scale factor 2. And then finally, we do a flip to give us our w of t. And so, same kind of shape, just flipped it across that vertical axis, gives us our w of t. And so if we want to verify if this makes sense, I can take a value here, say w of 0. I look back at my original definition that I have here. I'm going to substitute in t as 0. So that's x of -2 times 0 minus 1 gives me x of -1. I can compare that the values match up. I take a look at -1/2. I can see at -1/2 it should be equivalent to x of 0. So yes, indeed, this was done correctly. And we can see that w of t matches up with the relative definition that we had to x of t. So the one thing that we have to be very careful about, right? So what if we had taken this same problem, but instead we had done the flipping and scaling first, and then the shifting. Right, so in that case, I start from my original x of t I have up here. I do my flip. So we have, looks exactly like the original because we had even symmetry. Then I do my scale. Okay, so scaling, we're still shrinking in time by that 2. And then if I look at it and said, right, so I had a -1, so that means I need to shift it to the right by 1. And so now this is going to be at 1/2. And we can see in this case that it doesn't match up with what we had here. Right? So if we were to do a comparison, right, I just call this gamma of t. So if we were to look at, say, gamma of 1 is 1. If we look at x substituting in 1, that they don't match up. Right? So this is one of those things that is easy to mix up the first few times, right? Because you think, well, we're just doing these 3 things. As long as I do those 3 things, it's fine. But it turns out that the order that you do things actually does matter. And so there is a way that if you want to do flip scale shift, I'll mention that as well, because you might have learned something like that in another setting. I tend to suggest that you treat it as shift, scale, then flip, right? So I kind of remember it by being reverse alphabetical order that you're doing those 3 steps in. If you are someone who really wants to do flip, scale, then shift, you can do that. The exception would be if you rewrite. So like, let's say that you have this x of -2, t -1, like what we had before. If you were to rewrite it by pulling out that -2, then we can see if we compare the 2. Here we have our scale and our shift. Over here, right, so the scale was the same, but our shift is different, right? So if you rewrite it like this, where you can account for the fact that having that scale is going to change what your shift is, then if you really, really want to, then in this case, you could do your flip scale, then shift, and it is possible to do it that way. Or you just kind of stick with the definitions as we talked about, do shift, scale, flip, keep things as it was originally written, right? Completely up to you how you like to think about that. So one more kind of key idea that I want to introduce is actually going to result in a signal that we're going to use so much that you're probably going to get sick of hearing me refer to this particular signal. And where it's going to come from is by looking at that step signal that we talked about before. So our step signal, we have u of t, 0 for t less than 0, 1 when we're greater than 0, and it looks like this. So if we take and integrate the signal, we're going to take an integral minus infinity to t u of tau d tau. Right, so kind of a heads up, this is the thing that's probably going to trip up a lot of people. You're kind of used to whenever we do derivatives and integrals, it's always t. We're going to find out, especially in one of the topics that we're going to talk about, that you have t's and tau's, and you're integrating with respect to one of those variables. The other you treat like a constant. Right, so kind of getting used to the idea that t isn't always our variable of interest. It will actually change from time to time. Right, so in this case, so if we look at u of tau, and what we're doing is we're integrating from minus infinity up to t. And that t can change. So what this means is we actually have a couple different cases. So the first case is if that t is less than 0, then all we're doing is we're integrating over 0. And so integral of 0 is 0. Once we have t greater than 0, right, so now we can see that this integral becomes the integral from 0 to t. Our u of tau is 1. Gives us tau. Evaluate for tau equals 0 to t. It's going to give us t for t greater than equal to 0. And so we can define this to be r of t, the ramp signal. So what that's going to look like right, looks like a ramp. And so you could think of this in another way. Derivative of the ramp is the step. Right, so in that case, pretty straightforward to do that derivative integral relationship. The problem that comes about is that u of t actually has a discontinuity. Right, so if I want to do the derivative of u of t, right, for t less than 0, that's straightforward. For t greater than 0, that's straightforward. But actually at t equals 0, what is that derivative? Well, we're actually going to define a very special signal, which we call the Dirac delta function. Right, so this delta of t captures when we have this discontinuity, when we're taking our derivative. We're going to see that this delta function is going to come up a lot of situations. It's going to be a very powerful tool for analyzing different kinds of systems. And the way that we're going to sketch this is that this delta of t, we're going to draw it as an arrow because it's a very special kind of signal. It's infinitely small width, infinitely tall height, such that it has a magnitude of 1. Right, so kind of a weird sort of idea. Might not really make a lot of kind of intuitive sense what an impulse is, but where this actually comes from, and if I don't quite finish, I'll make sure to add the notes as well. Where we derive this idea is we kind of take and consider an approximate version of this. Okay, so essentially have this little rectangle shape here. Like so. And so if I had this small little rectangle and I was to take the integral of that, what I would get, right, so using similar kind of logic to what I used up here, we're going to have different cases. Right, so if I take the integral of this little kind of rectangle here, what I end up getting is something that's pretty close to a step, but not quite the step signal, right? Because we have this little bit of a linear region in there. And so where this idea of the delta comes in is we can take, say this looks pretty close to what I want it to be. So what if I was to take the limit as epsilon goes to 0? Then I could say that this integral is equal to my step. And so this is where we get this idea of this delta function. We're essentially taking the delta epsilon, making this epsilon width here go all the way to 0, making the height go all the way to infinity, such that that area there is 1. Right? So weird kind of idea mathematically, but we'll see that this is going to pop up a lot, allow us to do a lot of things. Yeah.
It's supposed to be like infinitely small.
Yeah. Yeah, so when we're actually working with it, we're just going to go ahead and use that delta of t. This is just showing you kind of the idea of where it's coming from, that we have this idea of something that is almost giving us what we want. We're going to kind of take the limit of it mathematically and say, well, if this went to 0, then hey, that would be exactly that step.